afternoon, everyone. My name is Mike Marr, and I'm with RAUGEO out of Leesburg, Virginia. This is a one-hour presentation titled Geothermal Piping Technology, and I'm going to be spending a lot of time on the ground loop heat exchange system. I'm not going to be talking too much about the inside equipment. This is going to be a presentation related to the outside borehole field. I'm looking to advance the slide here. I apologize, it's not advancing. Okay, there we go. And that's me. Here are a list of the learning objectives for the presentation. I'm going to be explaining the role of the ground loop heat exchanger and some of the physical demands placed on these pipes. The two common geothermal piping systems, high-density polyethylene and, as of 2008, Hdpe pipe material. We'll be talking about some of the joining methods for these two types of piping materials, some of the manifolding strategies, and then I'll wrap up with a list of reference projects. RAUGEO, just a little bit on RAUGEO. RAUGEO is a privately held company started in 1948, and we're having some 17,000 employees, about $3 billion a year in sales. Our three main strategic business divisions are construction, automotive, and industry. You can see that the geothermal program is underneath construction. We also have radiant heating and cooling, snow and ice melt systems, plumbing, energy transfer piping, and windows and doors in construction. Automotive, we're doing anything from injection molding of bumpers, body side molding, windshield trim moldings, and in industry, key programs would be office furniture for folks like Herman Miller, Steelcase Hayworth, IKEA, appliance division for Whirlpool, and we've got industrial developments. This is a residential model here, just a schematic, but I think most of the audience is commercial here, so I'll pull up the commercial one. And RAUGEO takes a three-prong approach to saving energy. We start off, as you can see here, with the windows and doors. We've got high-performance openings for windows and doors, so we want to start with utilizing those to reduce the heating and cooling loads for the building. Then we want to have smart choices for the source of energy, the geothermal, and then efficient means of distribution for conditioning the space, radiant heating and radiant cooling technologies. Just a quick disclaimer here that the information that I'm giving is as accurate as we know it to be at the time. I would direct you to our website that's listed there, www.na.raugeo.com. We've got a resource center there with all of our technical bulletins. So, geothermal earth energy systems. This is a blurb from the International Ground Source Heat Pump Association. And ground source heat pumps are all electrical powered units that are utilizing the relatively constant temperature of the earth for heating and cooling and generation of domestic hot water. And these are considered to be some of the most energy efficient systems compared to conventional heating and cooling technologies. The three types of or I should say the two types of geothermal fields are open loop and closed loop. We'll talk a little bit more about that, and then we'll be talking about some of the physical demands that are placed on these piping systems. Excuse me. On the open loop, we've got single well, dual well, and a pump and dump. And what we're doing here with an open loop is we are using the groundwater from the aquifer and pulling it up into the system. In the single well, you can see we're drawing up groundwater. We run it through the system and we bring it back down into the same well. Dual well, it's doing the same thing except when we're returning the water in a second well. And then the third is a pump and dump. We're drawing water up out of the aquifer and then we're pumping it in a body of water such as a river. Closed loop geothermal systems. Three main types: vertical boreholes, where we're going down hundreds of feet with say a 5 or 6 inch diameter borehole. Horizontal loop fields, where we'd be going down maybe 6 feet, 8 feet from the surface, and then a pond loop where we are utilizing a body of water in lieu of the earth for acting as the condenser for the heat exchange. The closed loop heat exchanger includes the loop itself. There's a grout that is used from the bottom of the boreholes all the way up to the top, and then often there would be an antifreeze solution, water treatment solution as well in a closed loop system. This is showing just a closed loop, some of the piping systems there on the left. Those are 2 coils of PEX-A pipes getting ready to be installed for vertical applications. On the right, we're seeing an Hdpe U-bend that's being dropped down a borehole. Some images on closed loop. On horizontal, that would be a commercial application on the left, down about 7 or 8 feet. We've got 3 circuits of piping running down. There will be a backfill of about 2 feet, and then another set of 3 circuits running down in that trench, and then you would have multiple trenches. The other images on the right at the top would be typical of a backhoe trench with a single circuit for residential applications. The middle one is showing a pit where we've got high-density polyethylene, and we've got slinky patterns of piping in there, maximizing the amount of pipe in that pit. And the bottom one, we're having a trench, and we're utilizing not only the bottom of the trench, but as you can see also the sidewalls of the trench. This is of mention here, energy piles. This is a technology that is in place in Europe. It's starting to come into the U.S. market. And this is a cost-effective means of being able to get circuits of pipe in the rebar cage prior to the pour for foundation pilings, caisson pilings. And you can see that on the image of the right underneath the building. This can be a modeled and calculated contribution of the heat exchange that can be supplied to the building. Generally, you're not going to pick up all the required heat exchange to satisfy the heating and cooling loads of the building, but we can make a contribution, and then the balance of the required heat exchange could be taken up by typically vertical boreholes. This is a helix coil, and this is a cost-effective installation where we are using an auger bit and going down about 14, 15 feet. You can see that the image on the left, you can see it stretched out. This is somewhat like a slinky. You stretch it out, and we're getting about 130 feet of pipe down in each boring, and then these would be tied together in a series, and they're spaced out about 10 feet apart. And depending on the location and the temperature and the type of soils, you have anywhere between 4 to 7 of these together in a series to generate a ton or 12,000 BTUs of heat exchange. I'm going to talk now about some of the physical demands that are placed on these piping systems. A little bit on the flexibility, impact resistance, abrasion resistance, 2 important factors there. Chemical resistance, and then temperature and pressure capabilities. On flexibility, you can see this is with a PEX-A pipe that provides very good flexibility for being able to uncoil the pipe and get it into a horizontal trench. You want pipes that are going to be unrolling easily for, in this case, high-density polyethylene going into a vertical borehole. You want to have flexibility, but at the same time you want to have a stiff enough pipe that you're not getting into kinking of the pipe doing insertion down a vertical borehole. Impact resistance is an important consideration, being that these are outside of the earth, these piping systems, and we want to have a strong pipe material that can withstand some rocky soil conditions, as you see in this image here with PEX-A pipes. You want to have physical properties that can safeguard against impact resistance or provide impact resistance and puncture load resistance. This is some images here with PEX-8 pipes, and it's a little extreme, I know, on the left, but it's showing you the durability of PEX-8 material in piping systems. As you can see, that heavy equipment, backfilling over the tops of the pipe with that heavy equipment. Now, on the abrasion resistance and punctual resistance with high-density polyethylene pipes, the Hdpe guidelines want horizontal piping of Hdpe to be in a sand bed. They do not want to have the rocky type of soil that you see in the image on the right, as it may create some damage and puncturing the pipe. Also, you want to be safeguarding against abrasion resistance, or have materials with good abrasion resistance and safeguarding against nicking up the pipe. In this case, you see an image of high-density polyethylene being inserted down a vertical borehole where you have steel casing. And why are these important applications? Well, if you could have a camera lens in a 6-inch diameter boring that's going down hundreds of feet after drilling, and you're inserting the pipe, you're not going down directly right in the center. If you've ever seen any of the insertions of these vertical loops, you're going to be working the pipe, and it's going to be coming in contact with the sidewalls of that vertical borehole. Grout is used on vertical boreholes, and the two main reasons for grout would be environmental and technical. On environmental, what we're doing is we're using a bentonite clay that aids in sealing the borehole from the bottom all the way to the top to prevent surface contaminants getting down into the groundwater, into the aquifer. The technical reasons for utilizing grout would be to enhance the conductivity of that borehole. Here's an image showing you grout after a few weeks, and you can see that it's still pliable, still moist. You don't want the grout to be drying out. That's why this bentonite clay, a special clay from Wyoming, is utilized. You can enhance the conductivity of the grout by mixing that bentonite clay in with silica sand. And with a higher conductivity grout, you can reduce the modeled borehole length for the project. Chemical resistance is, a consideration which both Hdpe and PEX-8 pipes have excellent chemical resistance against some of the cementitious grouts that are on the market. It also can be utilized with all of the antifreezes, methanol, ethanol, and propylene glycol. Temperature and pressure, you can see some ratings here. To the ASTM D2837 standard, you have a minimum of 160 psi, and generally it's up higher with Hdpe and PEX-8 pipes in the range of 200 psi. And you can also you can see at the bottom here with some PEX-8 pipes, some pressure ratings at higher temperatures, 100 psi at 180 degrees and 80 psi at 200 degrees Fahrenheit on PEX-8 pipes. So just summarizing in this section here, you want piping materials that provide good flexibility, impact resistance, abrasion resistance, chemical resistance, and temperature pressure capabilities. These are important for the longevity of the piping material. I'm going to be talking now about the two types of materials that are in the Hdpe standard. They are high-density polyethylene and cross-linked polyethylene, and specifically PEX-A. This is just an excerpt from the Hdpe standards. If you went to the Hdpe website, and it's of 2008, Hdpe recognized PEX-A into the standards. Prior to that, it was just high-density polyethylene. So high-density polyethylene is a thermoplastic material. That means that that material can be heated and molded together, fused together, and reheated and remolded over and over again. It's got a good durability. It's strong. It's got moderate stiffness to it, good chemical resistance. The operating temperature of it is, 100 to 104 to 140 degrees Fahrenheit. There is some slight derating that takes place on it over 80 degrees. Excuse me, I'm going to come back to that image again. What I want to point out is you can see that the polyethylene molecules that are in the piping material are free floating. So if you were to look at a piece of pipe, the molecule strands running along the length of that pipe would be just floating, if you will, and not being connected together. Some of the sizes for typical heat exchange pipe, 3/4 inch, 1 inch, 1.25 inch. Generally it's in IPS dimensions, iron pipe size. The U-bends are fused and welded in at the factory where the pipe is made, fabricated in a factory setting, not out in the field. You can see that fused U-bend at the bottom of the loop on the Hdpe coil on the right. There's two types of Hdpe materials. There's PE 3408 and PE 4710. The PE 4710 came out a few years ago because the industry wanted to improve the physical properties of the material, particularly in this area of environmental resistance to slow crack growth and punctual load resistance. This document, Plastic Pipe Institute, compares some of the physical property characteristics of PEX with high-density polyethylene. The second bullet there is particularly important on the environmental stress crack growth resistance and the resistance to slow crack growth that I mentioned, and the reason why the Hdpe went to that formulation PE 4710 I mentioned. I won't read this here, but this is just showing you again some of the tensile strength and elongation and environmental stress crack growth and resistance to slow crack growth between PEX and Hdpe. And in all of the categories there, the PEX-A is having a better characteristic. So PEX is, has an acronym. It just stands for polyethylene, cross-linked polyethylene, the X being the cross-linking. And what you can see here in the molecule structure on the right, if you remember the Hdpe, those molecule strands were free floating. With the PEX material, what we're doing is we're cross-linking those strands and connecting them together. So PEX is really Hdpe with the molecules cross-linked. And again, you can see the free-floating polyethylene or Hdpe molecules on the left there. We use an analogy of thinking of the piping molecules being like a picket fence, and with the cross-linking of those molecules being a chain link fence, which improves the characteristics that I mentioned for temperatures, resistance to slow crack growth, and chemical resistance and flexibility of the pipe. So Hdpe has recognized in their standard PEX-A, and I'll talk about that in a moment, but I just want to say there are 3 levels of PEX. There's an A, B, and C. It has to do with the production method of the PEX material. That's what differentiates between the A, B, and C. The PEX-A is a high-pressure peroxide, high-temperature method. When the pipe material is coming out of the extruder, the cross-linking process is started. It takes about a week for it to complete. The material gets quarantined, and then it goes into final QC inspection before going into inventory. The other 2 methods, PEX B and C, were producing Hdpe pipe, and then it's a secondary process for the cross-linking. There's a silane method, which is known as a moisture cure method, and a PEX C is taking the Hdpe pipe and as a secondary process running it through an electron beamer. It's known as the nuclear method, and that acts as the catalyst for the cross-linking. The PEX-A is considered to be the highest quality of the 3, and the reason being it provides the most consistent cross-linking percentages that we want to see in the material all the way through the pipe, which will be about 80 to 90%. cross-linking percentage of the molecules, and the sweet spot being 85 to 87%. And so, as I mentioned, if you go to the ISPA guidelines, you'll see that it's not just generically saying PEX, but it is saying PEX-A. And that has to do largely because of the connection method I'll talk to about. And again, the 80 to 90% being the optimal percentage for PEX-A materials all the way through the wall thickness of the piping material. So, you know, here are some of the temperature and pressure capabilities of the PEX-A pipes. And as I mentioned, 200 psi at 73 degrees Fahrenheit. And you can see we're actually having ratings all the way up to 200 degrees Fahrenheit at 80 psi. Some folks would say, well, you'd never see a geothermal system that would have those kind of temperatures. And that's true, but sometimes we see hybrid systems that could be integrated in with, say, a solar thermal system, which would be providing higher temperatures to the hybrid system. These PEX pipes have minimum quick burst pressures, and you can see here to the ASTM standard F876 475 PSF at 73.4 degrees Fahrenheit. RAUGEO actually internally contests the ductile failure to this ASTM D1599 at the 73.4 Fahrenheit temperature, and we are far exceeding the minimum of 475 psi in the range of 800 psi to ductile failure. This is what we're talking about, this test. It's called the Pent Test, and this is an ASTM test method that was developed by the Hdpe manufacturers when they moved from that PE 3408 formulation to PE 4710 I mentioned. What they wanted to do was prove the improvement in this area of slow crack growth. There's a test apparatus that you can see here that puts some force on the piping material. It's stretching it. There's a notch that's put through a cut through 50% of the wall thickness of the pipe material being tested, and then there's some slight heat putting on it to accelerate the testing. And what we're measuring is in terms of hours to failure, meaning breaking through 100% of the wall thickness. RAUGEO submitted some samples to the testing lab with the PEX-A material. We were interested in seeing how we would perform in comparison to this new PE 4710 material that I mentioned. And again, what we're doing is we are, with that weight force, we are stretching the pipe, and we are measuring in hours to 100% breakthrough, which would be a failure or leak in the piping system. So the PE 4710 failure time was 116 hours. That was an improvement of around 50 hours with the PE 3408 formulation. So there was an improvement. On the PEX-A material, after about 2,050 hours of testing time, it was decided to stop the test because there wasn't going to be a failure. But the purpose here is showing again the physical properties of PEX-A material to even the newer formulation of Hdpe in this area of slow crack growth. So that allows PEX-A materials to be used in a horizontal application without having to have the need of that sand bed that ISPA wants the Hdpe pipes to be bedded in. And that would be a savings of time and material by not having to truck in sand in preparing the bed for the pipes. Here on the left, you know, again, a project where sand is being trucked in for sand bedding on an Hdpe project. You can see the sand bedding of it, of the Hdpe pipe, and then again, the PEX-A pipe material can use the native fill and have rocky have rocks in the soil, and within reason, of course, not big boulders, and being able to have a material that safeguards against puncture load. Flexibility of PEX-8 pipes. You can see the modulus elasticity at 86,000 psi compared to the Hdpe material. Hdpe gets down to a bend radius about 25 times the OD of the pipe. Because of that cross-linking of the PEX-A material, we can get it down to about 5 times the OD without kinking of the pipe. So here are showing you on different pipe sizes the radius and diameter with the PEX-A pipe. As I mentioned, it's 5 times the OD of the piping material. Again, here is 2 coils of PEX-A pipe, just showing the flexibility and ease of uncoiling the pipe material. Similar image for a horizontal application for trenching. The tensile strength for the Hdpe and PEX-A, the Hdpe tears about 40% elongation, and the PEX material is about 4 times that, 400%. So when we take like a 1-foot section, we'll stretch it out to about 4 feet, and the pipe will get thin and snaps, but it gives about 4 times the original length for failure. Back to that bend radius. You know, we can, as I mentioned, we can get down to 5 times the OD without kinking of the pipe. If we put a little heat to it in a controlled environment, we can get down under 3 times the OD of the pipe dimension. And what we're seeing here is a U-bend because of that bend radius, that tight bend radius. We are able to take the joint out of the vertical loops where the Hdpe is welded, as you can see on the left there. We also have coil pipe in PEX-A for horizontal applications in different sizes and different coil lengths. Here's an illustration on the 1-inch piping material, and here's the U-bend that's formed in the factory setting with a bending table with radius fixtures that has some heat. We've got a process for controlling the wall thickness in the radius area of the U-bend so that the wall does not get too thin. After forming that U-bend, there is a casting operation of this probe tip, this white probe tip. It's a glass polyester resin. What that does is it provides a very neat system for being able to nest a U-bend in a U-bend, attach the 2 of them together with 2 Allen bolts, and because of the nesting, we're not changing the diameter when we go from a single U-bend to a double U-bend. And you can see that nesting on the bottom image here. And we have different coil lengths that equate to borehole lengths: 210 feet, 260, 310 feet, 360. And then we've got 1¼ pipes that have coil lengths up to 510 feet. Here you can see the 2 U-bends being nested and the installer fastening those probe tips together. They come out to the project site on a pallet as 2 single U-bends with the white probe tips at the ends. We're a big advocate for utilizing pipe spacers along the length of the pipe. What that does is keeps the U-bends up close to the perimeter of the borehole where you want it for heat exchange. And it also equally spaces your 2 supplies and 2 return pipes to minimize thermal interference. And the image on the right there is showing the 2 individual coils. It's hard to see, but at the bottom left there, that's the nested 2 white probe tips, and just getting ready to be inserted down a vertical borehole. Here's the pipe spacer that I mentioned, and the center of that spacer allows for the grout pipe, known as the Tremie pipe, to have all of those spacers preloaded on and the grout pipe placed in the center of that nested configuration, and slide a spacer on about every 6 feet and snap on and drop the loop down, and slide another spacer on, drop the loop down, etc. So why are we nesting? And a proponent of W bends is because we're picking up additional heat exchange. Generally, the heat exchange increase is about 20 to 30%, and that reduces the borehole length for the project in the drilling costs, grouting costs, and also compresses the construction schedule to allow the contractor to be on and off the project in a shorter period of time with less drilling. Testing's been done many years ago over in Germany. We did some testing over here. Actually, on our property site, it was an independent test with an engineering firm. We had 4 boreholes, a single loop of Hdpe, a single loop of PEX, a W bend of PEX without the spacers, and then a W bend with the spacers. That testing was done back in 2009. This is showing the test apparatus. If you've ever been involved in a commercial project, this is typical equipment that you'd see with a thermal conductivity test. That would be a 48-hour test where we're putting electrical impulses into fluid into a water and measuring the temperature change over the time. So there's a full report here. If anybody wants a copy of it, just throw a question up, and if I get your email address, or you can send me an email, I'll get the report out to you. But you know, this report is showing that in the area of the W bends with the spacers compared to the single U bend of Hdpe in a heating dominant project, where there'd be about a 24% difference in heat exchange, reduction in heat exchange, and in a cooling dominant would be typical of commercial application, a 30% reduction. Testing has also been done by Oak Ridge Laboratories as well, validating these additional heat exchange for the W bends. So what does that mean? If you have a 25% additional heat exchange, it means that in this case you're able to take a couple of boreholes off of the project. So some of the reasons for the W bend, you know, reducing the drilling, the number of boreholes as mentioned. You know, we can, you know, also have some redundancy on a true home run system where each U-bend would be possibly be running back to a balancing manifold, which is more typical for a residential application. So some of the advantages of the PEX pipe material being summarized: flexible material, better toughness for puncture load resistance, crack growth resistance, temperature capabilities, higher temperature ranges, and the elimination of joints in the borehole. I'm going to move now over to some of the joining methods of the Hdpe and PEX pipes. The Hdpe is typically fusion. I mentioned it's a thermoplastic, and so it would be heat fusion with heat plates in the range of about 500 degrees Fahrenheit. So you have socket fusion, butt fusion. You can also have electrofusion and stab fittings with the Hdpe pipes. The cold compression fitting system for PEX pipes, which is the center image, which is the one that is from RAUGEO, cannot be done with the Hdpe pipes. We're going to be expanding the inside diameter of the PEX pipe. If you were to do that with the Hdpe, you're expanding it, you'd be cracking the piping material. Also, PEX pipes can be joined with the electrofusion, which is on the left, and scab fittings on the right. Because of the cross-linking process of the PEX pipes, you no longer have the ability of doing direct heat fusion. The PEX is not a thermoplastic; it becomes a thermal set. And this is just some images here on socket fusion with Hdpe. It's really, as I said, melting and joining the two materials together. It's almost like welding, if you will. A fusion weld, fusion joint, and as mentioned, you would have joints at the bottom of the U-bend loops. Here's some butt fusion with Hdpe pipes, and you're joining these two under some pressure and holding the two pipe materials against each other after they've been welded. I know this is a little extreme, but Hdpe does not want to have a fusion taking place, since these plates are electrical plates, in an environment with water. With PEX-A and compression fitting systems, it's fine if it's wet out, and it's fine if it's dirty. It's another area with the Hdpe fusion. You want to make sure that there's no dirt at all on the piping materials prior to the welding. This is just an excerpt from the Hdpe standards saying that they don't want fusion taking place if there's water in the trenches. So on the RAUGEO method of joining, which is this cold compression fitting system, it was introduced in 1988. It really is a bulletproof fitting system. It can be buried in the ground with the fitting in the sleeve being wrapped and protected with a waterproofing sleeve or taping material. You don't need any heat. No electricity is being used. Again, it's fine to be joining the pipes in rain if it's cold. Minimal skill level is required for this joining method. And this is the standard. There's two pieces to this fitting system. There's the fitting. In this case, you see a 1-inch coupling on the right, and then on the center there is a sleeve that's going to be pulled up over the pipe and the fitting to complete the joining of the fitting. So just go through here, and this was a live audience, so I was in front of you. I would actually go through an example with the fitting system, but here I'll do it with slides. You can see here that there's ribs on this fitting. There's a large rib before the collar that actually acts as the stop when we expand the inside diameter of the pipe and then we insert that fitting. That last large rib before the collar is actually a stop. Those ribs, when we pull the sleeve up, those ribs are actually going, if you can see, being embedded in the inside wall of the pipe. That's why it's a really secure joining method. If you remember the tensile strength test I was showing you, where we get about 4 times the length of the piping material. We're putting about 800 pounds of force on when we're stretching that pipe out. And again, it's the pipe that gets real thin and snaps and fails, and that's what we want to see. It's not at the joint. So we want to, just going through the illustration of that joining method, have a nice clean cut of the end of the pipe. There's an expander tool that has a head that can be removed for different dimensions. You would put the sleeve on before expanding the pipe. That's in image 2 there. As you can see, the expander head is inserted in the inside diameter of the pipe. What we're doing is we're compressing that down, and it spreads that head and opens up the inside diameter of the PEX-A pipe. You can see in image 4 the fitting has been inserted. And if that sleeve wasn't pulled up, I just want to mention that after about 10 minutes, it would be extremely difficult to be able to pull that fitting out of that PEX-A pipe, because I mentioned that the PEX-A pipe is a thermal set. What's happening is that pipe is trying to come back to its original extruded ID dimension. So considerable force is being applied to that fitting before the sleeve is pulled up over the pipe in the fitting. The second step is there's a ratchet that's geared. The ratchet, as you can see, has jaws, and what we're doing is we're going to ratchet that sleeve up over the pipe in the fitting, and you can see the finished connection in slide 6 there. And as mentioned, we want the fittings to be protected with a heat shrink sleeve or waterproofing tape. And here's waterproofing tape you can see in the image on the left with some branch tees. And as mentioned, the other two methods for PEX-A would be electrofusion couplings and stab fittings. The stab fittings you can kind of think of almost a shark bite. On either side of that stab fitting, there are two O-rings, and the PEX-A pipe gets chamfered down about 1/8 of an inch, and then when you insert it in, it goes underneath those O-rings. So you've got those two O-rings on the OD of the pipe, which is where you want to see it, just because with any polymer material, with temperature changes, you're going to get some slight expansion and contraction. You've got the seal of the O-rings going with it. On the electrofusion coupling, there are wired elements on either side there, and we're putting, there's a positive negative pole. There's a machine that's going to be putting voltage current to that fitting, and it's going to be kind of molding around the PEX-A pipe to secure the joint. There's a barcode there that gets scanned so the machine knows how much to apply and for how long. It takes the guesswork out of it. So in summary here on the connections, Hdpe is generally done with the fusion, heat fusion. Again, the stab and electrofusion fittings are applicable for the Hdpe pipe as well as the PEX-A pipe. And then there's the cold compression fitting systems that I've mentioned that's supplied by RAUGEO. And again, it's very fast, and the skill level is very low. It's a one-man process. With the heat fusion of the Hdpe pipes, generally it's a two-man operation, and the skill set is higher because of the potential risk. I'm going to talk now about the manifolding strategies for PEX-A pipe material and Hdpe that's typically done in the market. Talk about a reverse return in closed buried headers versus balancing manifolds. With the high-density polyethylene, typically the boreholes are tied together, if you will, with horizontal piping in what's known as a reverse return headering pattern, meaning you can see here the first borehole on the left. You can see that the return from the heat pump going back out to the field is the first into that borehole, and then the supply to the heat pump coming out is the last in. So it's first in, last out, second in, third to last out, etc. And you want to have the lengths of those boreholes in the piping material to be within about 5% plus or minus 5% lengths of each other to minimize any short circuiting in the flow between all four of those boreholes. Just a sidebar here, in this particular circuit of 4 boreholes, you have in the area of about 34 welded or fused connections with the Hdpe pipe. And it's just showing you some illustration of the headering with that fusion of the tails, if you will, from the boreholes with the Hdpe pipe. When you're purging this type of a reverse return, you're purging the entire circuit of how many boreholes are on that circuit. RAUGEO is a proponent of having access and control of the borehole field. And access meaning being able to get to balancing manifolds, and control meaning having balancing manifolds with the ability to isolate down to a single circuit. And a single circuit could be just a U-bend in a borehole, which is generally done with residential applications, or it could be a circuit could be representative of a borehole itself by utilizing 2 branch tees at each borehole, and we'll talk a little bit more about that. But this is more of a commercial grade headers. We fabricate these also at the same plant where we extrude and fabricate the U-bends of the PEX-A down our plant in Alabama. We fabricate these all the way up to 20 continuous drops, 10 GPM per circuit, or if you will, up to a capacity of 200 GPM in a 20 drop header set. These would have, flow gauges. In this case, they're Polyethylene flow gauges with a bypass pin to get a reading. You set it, and there's isolation valves, as you can see here, with the traticator with the temperature and pressure gauges, and then mounting brackets. And here's some image inside a mechanical room of headers that have the Polyethylene flow gauges, and here you're seeing the pair of them, and a supply drop and a return drop would be representative, in this case, a circuit that would have the ability of controlling a single borehole. And again, we put all these monies into these outside geothermal heat exchange fields, and we feel it's very important to have access to the field and have control of the field. If you're ever needing to, in this case, you can isolate down to a single borehole. Just another image. These balancing manifolds can be located in a mechanical room, depending on the proximity of the borehole field, or in some cases, in a precast manhole vault. You'd have the balancing manifolds installed inside the vault, and then you would have, say, 4-inch or 6-inch mains, supply and return mains, coming from the vault, going into the mechanical room to the pumps. So that ability of being able to set the flow of each borehole, now you don't have to be concerned about this plus or minus 5% length that I mentioned in the reverse return headering. In this case, you can see there's some different borehole lengths, 260 feet. Might have ran into a problem, possibly a lot of water. So you do have the flexibility of being able to short one borehole and put possibly some additional borehole length to one of the other boreholes. This is just showing you a Hdpe application where a bunch of additional pipe was thrown in to equalize up the pipe lengths that I mentioned to eliminate or prevent the short circuiting of the flow between the boreholes and the circuit. So we talked about reverse return headering, typical of Hdpe, in balancing manifolds, which is the strategy that RAUGEO advocates. With the balancing manifolds, you don't have any fusion connections or any of those joints. You have a fewer number of fittings. In the case of commercial applications, just note we're controlling each borehole by having 2 branch tees at the tops of each borehole. And when you start your horizontal piping, we take those 2 supplies and 2 returns in each borehole, and with those branch tees, we'd have a 1-inch, 1-inch by 1.25" supply and a 1-inch, 1-inch, 1.25" return. So now you have a single supply and return coming from and going to each borehole back into the balancing manifolds, creating a circuit. It's just another advantage of that, in addition to being able to isolate down a single borehole, is that the flushing and purging of the system is simplified. We're doing one borehole at a time as opposed to an entire circuit, and it's not unusual in commercial applications in a circuit of Hdpe pipe or reverse return headering to have as many as 8, 10, 12 boreholes on that circuit. If there's ever a leak in that circuit, you can isolate it down to that circuit, but you don't know which borehole it is, and then you go digging up and start looking for it, hoping that it's in the horizontal fusion and not in one of the boreholes. So I want to talk about a couple of reference projects here. This happens to be a Toyota dealership. getting installed with PEX-8 pipe. Here's two of the branch tees that I mentioned, taking the 2 supplies and 2 returns and stepping up to a 1 inch and 1/4 supply and return. That happened to be for a school project. Excuse me, this is for a bank project with the PEX-8 pipes of double U-bends. You can see the trimming pipe. In this case, the trimming pipe was not put between the spacers. The trimming pipe was dropped down first, and then they dropped the double U-bends with the spacers. This is a winery project in Pennsylvania. This is a new construction builder project. For some of the smaller jobs, instead of doing those larger precast vaults, you can have these quasi boxes, kind of utility box, and locate the balancing manifolds inside of there. And these can be closer to the borehole field outside as opposed to in the mechanical room. And then you would have, you can see here, your main supplies and return 2-inch supply and return coming off of the manifolds going into the mechanical room. This is a fire station in Loudoun County, Virginia, getting installed with PEX-8 pipes. That's the horizontal piping. This is a residential project in Colorado with multiple circuits in a trench. It's another residential project with PEX-8 pipes. This is a community center project that's got a wider trench of horizontal piping. This would be layered, be 3 circuits down, 2 feet of backfill, and then another circuit, or another 3 circuits down the length of the trench. It's more typical of residential backhoe trenching. I'm just about through. I just wanted to talk for a moment about the Arcadia University project. This was a student center. You can see the quad area there for the students where they also played lacrosse. And this project was originally designed as 50 boreholes of Hdpe. The engineer was Benoni out of Philadelphia. Here is the original design. You can see the 50 boreholes. There are 5 circuits of 10 boreholes per circuit. And so you can see the each trenching of the 10 boreholes and the reverse return headering, this supply and return off of each trench going down into the building, into the mechanical room. RAUGEO was in touch with the general contractor before it got awarded out to the subcontractor driller and asked if they'd be interested in a proposal with the RAUGEO W-bend PEX-A materials that could reduce the size of the borehole field and potentially save money on the project. This is the redesign. We did size it down to 42 boreholes from 50 boreholes originally, and instead of 400 feet, 300 feet. And so what we have here are 42 boreholes where we are using those 2 branch tees of each borehole, and we're having 1 inch and 1/4 supply and return from each borehole. Going down, you can see on the left of the field there, kind of the northwest corner, that's the vault. And we had those commercial grade balancing manifolds inside that vault, 3 sets of them, a set along each of the long wall of the vault and one on the back side of the vault. Those being tied together, and then we had 6-inch mains coming out of the vault, a single 6-inch supply and return for the vault going back into the mechanical room. So you had the ability now, if ever needed, to access into the manhole cover of the vault, which was located about 18 inches down below grade with a blue ball, so you could locate that manhole cover. And you had the ability of going in and isolating down to a single borehole if there was ever an issue, say borehole 25, and shut off just one borehole and marginally impacted the performance of the field as opposed to if it was the original design and you had a leak, you could isolate down to a circuit of 10 boreholes. You'd have to close or shut off that complete circuit going in for researching, trying to find the leak. The other thing here is that with this redesign, with the PEXA materials for the 42 boreholes, there was a $50,000 savings compared to the low bid of the Hdpe design. And that $50,000 is after having the cost of the vault and the balancing manifolds that I mentioned in this redesign. So in summary here, I explained the role of the ground loop heat exchanger and some of the demands placed on the pipes, the two types of materials recognized by ISHPA, the Hdpe and PEXA materials. We spoke about the joining methods, heat fusion, electrofusion, stab fittings, and then the one RAUGEO supplies and advocates is the cold compression fitting system. And then we talked about some of the manifolding strategies of these heat exchanger fields, and then wrapped up here with a list of the reference projects. So that's the end of the presentation. I think I'm pretty much on time here. And I'm open to any questions that anybody in attendance may have. Louis, you still with me?
Yes, I am still here. Thanks for. Can you hear me now, Mike?
Yeah. Okay. I was like, holy cow! I hope I didn't. I was talking for an hour and lost audio or something. Yeah.
No, we did get a couple of questions come in. Most of them had to do with the pressure drop in the pipe and whatnot. So I will get some, either a link to the website or shoot you over a PDF of the pressure drops. That's pretty straightforward. A couple people have asked for the slideshow. Is this something that's available on the website, Mike, or something that you're able to send out?
Actually, I can send it to you as a PDF, Louis.
Okay.
I don't know if you want to be the gatekeeper to send it out, or if you want to direct anybody to me with my email address, which I'd be glad to give right now, and I'll just send it to them directly.
Why don't you go ahead and send it to me, and then I'll just assemble a list of all the people that are looking for it, and I can send it out to them with the pressure drop and what some of the other questions that were asked.
Okay, very good. Any other questions? And again, TEC, HVAC Solutions, is our distributor partner in the Chicagoland market. We've got some projects with this system installed in the area. We've got some that have been designed here recently, waiting to be installed. And we do provide the design support, not only for modeling of the sizing of the borehole field, but we do also provide drawings and schematics, that get supplied to engineering firms. Like in the case of the one I showed you with Arcadia University, we worked quite closely with the Pannoni, the engineering firm, to provide them with a lot of the drawings that got incorporated into their stamp set, as well as technical calculations. Is that it for the questions, Louis?
Yeah, I think that sums up everything we've gotten so far. If no one else has any other questions, I'm going to shoot my email into the question box real quick. If you guys want to send anything comes up, feel free to contact me, and I can get in touch with Mike as well. Or if you have any questions about projects that have come up or whatnot, we can go. Happy to help you with there and get Mike involved as well.
I'd be glad, on that point of the projects, I'd be glad to send out the CSI 3-part specs that we have, for our system, as well as specs of projects that have already been installed with our system, and the drawings, the specs and the drawings. I mean, we've got quite a few commercial projects that I can supply details on if anybody's interested.
Great. Well, thanks for your time, Mike, and if you can send me over the presentation, I'll get that distributed. And thank you all for joining us.
Yeah, thank you, everybody. Have a good rest of the afternoon. See you, Louis.
Bye.
Bye.